Did you want to promote Kendra to panelist?
I did. She hasn't.
Oh, it's not cooperating.
Yeah. Well, Kendra, I will try that again just in case more. All right. I think the person has to accept the promotion.
Oh, okay.
Promotion. So there she is. All right. I started recording, so sorry, Jules, you got to cut all that out. Hi, everybody. It's Friday. It's April 15th. Thank you all for attending. I think you got a couple more days for your taxes. So that's what my mom says. She was doing them last night. Like, isn't that due tomorrow? Anyway, hi, everybody. Welcome to this Friday's, the April edition of Chestnut Chat. I am thrilled to introduce Jen Santoro and her student Alec Henderson from Villanova here out of Pennsylvania. And this topic is of great interest to me as we move forward in terms of restoration and reintegration of American chestnut. We have a lot of questions about prioritization of sites. What sites are going to be suitable for reintroducing American chestnut? What sort of parameters can we define as being the most useful for people to select the most appropriate site to put these trees in? As with a lot of things, chestnuts do best in the right location. So location, location, location. So this is a big topic that's near and dear to me. And Jen was actually a previous intern with the American Chestnut Foundation. Was that 2013? I got it. All right. Sometimes I get the history right. She was with the Virginia chapter and has been involved with the foundation for a while. So I got a little ahead of myself. I didn't do any of my housekeeping. So I'm Sarah Fitzsimmons. I work for the American Chestnut Foundation. I work out of the Penn State Partnership Office. So I'm in my den right now, but I'm in State College. We are recording right now, so anything that you say in chat or in the Q&A, that's going to be recorded. And what we do is we download a transcript of the chat and the Q&A. We put that up on our website. We download a recording of this and we put that up on the YouTube. All of that is collated on our Chestnut Chat website that Sharon, who is also on here. Hi, Sharon. Thanks for collating all of that. So all of this is recorded and will be available for you afterwards. Jen was not an intern when she was 12 years old. She was an intern in 2012. So I don't know, in her 20s, I imagine. Yeah, so if you have a question, please put that in Q&A. And again, Q&A is really interactive. You can upvote questions. You can give it a thumbs up, and that means that it puts it higher on the queue. You can answer the questions as well if you have something to say on that. If you just have witty banter, if you do have a question, you can put that in chat, but it's harder for us to keep track of it. So put your questions in Q&A, put your witty banter and comments in the weather report in the chat. With that, I will turn it over to Lisa Thompson to introduce our speakers and say a little bit more about where we are with the foundation and get things started.
Hi, everyone. It's almost Earth Day, so I always look forward to that in April as well. So we'll be celebrating and probably next weekend with a lot of events that we're going to attend. So that's exciting. I'm really excited about today's topic. Habitat suitability is critically important, probably more so not knowing where not to put the chestnuts. So I'm hoping we're going to learn about that today. Disqualification is just as important as qualification, but really excited to have Jen and Alec today. I'll let them introduce themselves. But I just want to thank everybody for coming. We have a couple more people hopping on, over 100 participants. So thank you so much. We also have Bill Powell, who is leading the Transgenic Chestnut Project on this Chestnut Chat, so maybe he can answer that transgenic question that we get every time himself. So thanks, everyone. Jen, are you going first? Okay, take it away. Thanks, everybody.
I am. Thank you, Sarah. Thank you, Lisa. I really appreciate it. And on behalf of Alec and myself, thanks everyone for showing up. I think 100 is close to the largest audience I've ever had. So that is awesome. Really appreciate the chestnut enthusiasm. Chestnuts and geographic information systems are the two loves of my life. So using GIS and some of these habitat suitability models to look at where to replant chestnuts has been a passion project of mine for almost the past decade. I'm coming up on my 10-year chestnut anniversary, I think next year, from my internship in 2013. So I'm going to share my screen. Let's make sure that works and get PowerPoint going here. Look good, everyone?
Looks great, Jen. Thank you.
Okay, perfect. It's not like I've been using Zoom for the past couple of years.
Every day for 2 years.
I know, right? So welcome. Alec and I are going to talk about our work, habitat modeling for American chestnut. I'm going to start with the first half of this presentation and talk about some of the background information. So what I'm going to touch on is some of the reasoning why we tackle this work, some of the background on the modeling, and Alec is going to tell you about what we've actually been doing, great maps, great results, since he's largely been the one doing the actual GIS and modeling work. This is part of his senior thesis at Villanova University. I think he's got about 4 more presentations of this work geared up in the next 2 weeks. So this is his Chestnut Chat is his debut for presenting the full results for these models. Thanks again for the Chestnut Foundation for having us. And I'd also like to thank the Villanova Department of Geography and Environmental Science, where Alec and I both are, for supporting this work and just being really great folks to work with. So a brief introduction on me. I won't go too into depth. Obviously, I love chestnuts. I'm a visiting assistant professor at Villanova. I've been there since 2019. I primarily teach geographic information systems, or GIS, courses at Villanova, but I am a forest ecologist by study. I've got 2 master's degrees from Duke University, which is where I got introduced to chestnuts, where the chestnut bug bit me, and I've been preaching the word of chestnuts ever since. As Sarah mentioned, I was an intern with the Virginia chapter in 2013, and you can't go hiking with me anymore because I stop every 10 feet to point out a new chestnut. So I've been hunting for chestnuts from North Carolina all the way up to Vermont. It's an addiction. I'm going to let Alec unmute for a minute while he introduces himself, and then I'll take it back to talk about the modeling background.
All right, hello everyone. My name is Alec Henderson. As Jen mentioned, I'm a senior at Villanova, majoring in environmental science and with a minor in computer science, which has helped with some of this modeling stuff. And this is, a lot of this research is with my senior thesis on American chestnut distribution in Pennsylvania. This is the first of 5 presentations that I'm giving in a week and a half, and also the longest. So excited to get to talk about this work. Got invested in the chestnut world as a sophomore 2 years ago, doing an independent study with Jen on the same topic, and then I've been hooked since.
Awesome, thank you, Alec. So lets me click to the next slide. I'm glad to hear you're hooked, because my singular goal in life is to get more people addicted to chestnuts. All right, so let's dive in. I don't need to reinvent the wheel here. Many of us know the tragic tale of chestnut's demise, the chestnut blight invasion. It's been called the greatest ecological disaster to strike the world's forests because chestnut was just such an important tree in our eastern forest ecosystem. Numerous reasons for this that span ecologic, economic, and cultural reasons. So we're all pretty familiar with chestnut as a very reliable mast tree with nutritious nuts. These were great for wildlife, but also livestock feeding, especially in the farms of Appalachia. Chestnut had a huge cultural and economic importance to farmers who were feeding their livestock with very free and nutritious chestnut nuts. Chestnut was a fantastic lumber tree that grew quickly. So it was used for a lot of building projects, all different kinds, housing, roofing, lots of forest and timber products. It had rot-resistant wood, so it was used as fence posts a lot. It tended to grow on poorer sites. I probably should have put quotation marks around poorer. It did well on some of those sites that other trees just did not perform as well on. So chestnut had a bit of an advantage on some of these poorer sites. And I think we're taking advantage of that trait to plant new chestnuts on reclaimed mine sites. It tends to do pretty well in those soils that aren't seen as super great for other species of eastern trees. And of course, it was a contributor to species diversity of the eastern forests. On the East Coast, we boast a very high species diversity in terms of trees. I'm very proud of that fact. I'm from New Jersey, I'm from the East Coast, and I love our eastern forests. And losing chestnut was a hit to that species diversity. So it's really not hard to see why restoring chestnuts to its former glory is a huge priority for TACF and all of the chestnut enthusiasts that are in this chestnut chat right now. So I grabbed this screenshot right from TICF's website to highlight something about TICF's mission that really motivates me to continue with the modeling work that Alec and I will be speaking about today. So while creating this blight-resistant tree, whether that's through SUNY ESF's work with genetic modification or through back-cross breeding, that mission is front and center for TACF. It's clearly important if we're going to get anywhere with restoring chestnut to the landscape. But that next step of restoration is also built into TACF's mission. And that's where I feel the modeling work can really help. So it's not just about the single species of tree. TACF's mission centers around restoring ecosystems, enhancing biodiversity, benefiting wildlife and society, and really restoring entire forests. So I've brought up this portion which I highlighted to restore this tree to native forests along the eastern United States. And this snippet from the Restoring a Species page on TICF's website, where I highlight phrases like long-term commitment, biodiversity recovery, restoration of an entire ecosystem, to really nail home the point that it's not about a single tree, it's about an ecosystem. It's about maintaining ecosystem resilience in the face of climate change. It's about chestnut's importance as a single species, but also its contribution to the larger ecosystem. So with that kind of framework in mind, I want to get into some of the modeling work, why chestnut restoration is so important, and how our models can help. So the main point here, restoration does not end with a blight-resistant tree. We've got to figure out where, or as Lisa mentioned, where not to put it on the landscape. Once we have that blight-resistant tree, and of course, genetic variation from across the chestnut's range, where do we put it? The process of breeding these trees has certainly been a labor of love. It's also been time-consuming and costly. So what not to do is to grab a handful of these blight-resistant chestnuts and start flinging them into the forest to approach replanting that way. I think I'd give Sarah a heart attack if I suggested that we do that. So we're not going to do that. We need to be strategic about where we plant these new seeds in the forest. Just like TACF has been strategic about siting chestnut orchards and doing a lot of other work in breeding. We need a good site that's front and center. So we want to give these chestnuts the best shot at success locally, while also maximizing its geographic range regionally over which we plant them. So this problem is inherently spatial, something I like as a spatial ecologist. Location is important, and we need to think about both the very local scale and the regional range scale as well. Oh, I forgot to bring up my, my bullets. So we do want to give chestnuts the best shot at success going forward. There's already a lot of work that's being done to this end, from Georgia to Maine, all across chestnut's range, with a lot of great Chestnut Foundation partners, volunteers, universities, etc. So everybody has a role to play in this work. I had mentioned that this is a species-specific focus here. We are modeling American chestnuts, but we are taking into account its ecosystem level benefits. And plenty of small-scale experiments to study really important conditions for chestnut habitat are already taking place. I grabbed this photo right off of TACF's website of a planting in northern Indiana. And this is looking at, let's see, species mixture compatibility. So does chestnut grow well with other species like oaks, maples, tulip tree? This is really important to know if chestnut is going to be a component in eastern forests again. Other experiments are looking at growth rates. A US Forest Service and University of Vermont study in the Green Mountain National Forest has looked at cold tolerance and growth under different levels of forest canopy. I'm involved via my work at UVM and my doctoral dissertation in a study that partners with Dartmouth College in northern New Hampshire that looks at how chestnut survives north of its typical range to assess functionality given a very likely warmer climate future. Other work has studied planting stock, things like do we plant seeds versus bare root versus tubelings, and the tree density or the spacing between these trees. All of these are very important to study. They're at the hyper-local scale. They do consider site, but they're critical to figuring out the best way to restore chestnut to the landscape and address this restoration at local levels. But what Alec and I are going to tackle is a bit of a larger scale than that. The broader question of good site at a larger scale is also important. What if we want to know good chestnut habitats statewide to make broad planting recommendations for Pennsylvanians, for Vermonters, for North Carolinians, for New Jerseyans? How can we efficiently select these best sites or these habitats for future chestnut reintroduction plantings over this large area all at the same time? So knowing where that good habitat is over that larger area is the first step to narrowing down our focus on those good areas and make more local site-specific recommendations. So like Lisa said, we're eliminating some of that not great habitat in order to focus on the better habitat. So the local scale is super important. We can't go forward without it. That makes up the second part of our study. Alec's going to talk about a more local model that we ran. So it really comes down to an exercise in location and spatial scale, looking at things from the big picture, perhaps a statewide lens, but also a really local lens. An individual state park is what we're going to talk about. So before I turn it over to Alec to discuss that, I'll provide some background on the models we're using to accomplish this with, and Alec will then describe our specific research study in Pennsylvania. So modeling can be a thorny beast, and what I want to attempt here is to break it down so that folks at every level, whether you're an experienced GIS analyst or you've never touched modeling before, can understand the process we're going through. So we'll get started with the general idea of how we model habitat in the first place. The first thing we need to know is something about the environment or habitat in which our species of interest grows, and also how that varies across the landscape. So if we think about a fairly simple environmental variable, elevation, that varies across the landscape. The elevation where I am here in Delaware County, Pennsylvania, is quite different than Sarah's elevation over in State College. So we're in the same state, we're only a couple hours driving distance apart, but we have different elevations, and that variation matters. So knowing where things are and how they change, that's our first step to a habitat model. And this is because certain ranges within these characteristics determine where good habitat is located. A chestnut might grow better at higher elevations by Sarah than it will down in the lower elevations close to the Delaware River by me. I like to think of this as if anyone's gone hunting for morel mushrooms, you have certain habitat characteristics in mind. You're looking for places near streams in a forest with elm, ash, and oak trees. You've got this search image. You need to narrow down your habitat to a place that looks like that. So a model like I'm describing would highlight all the sites that have elm, ash, and oak trees and are near streams to really hone in your morel hunting success. We can do something very similar for chestnuts. We bring in the model itself, and the model is using both a combination of statistics and GIS or spatial analysis to predict the suitability at every given location across the study area for American chestnut. I won't go too deep in the weeds with the statistics today. We could get very fancy with that, but I don't think it's necessary. But broadly, these models look at where the chestnut occurs, what the habitat is like at that site of occurrence, and it tries to recognize patterns and find similar sites with similar characteristics in other places. That, by logic, should also be good habitat for chestnut. The utility of these models is that they're very useful for iterating over large areas. So Alec and I have tackled the entire state of Pennsylvania. And I included this Venn diagram in here to show a simple picture of what we're looking for. Perhaps we can isolate good soils, good elevation, and good rainfall amount for chestnuts. The intersection of those three variables is the ideal chestnut habitat. It's got 3 for 3 in terms of good habitat characteristics. Another thing I like to think about, and maybe this is a little cheesy, but hopefully some of you can relate, is thinking about ourselves as an example for modeling suitable habitat. All of us have habitat preferences. I, for example, like a good solid winter. I like snow, I like to cross-country ski, and I'd like to be in a place where I can do that a lot. Other people want to avoid the snow entirely. And maybe there are a few of you in this Chestnut Chat who have that take on life. So you and I would not have very similar habitat preferences based on that snow criterion alone. I can add a lot of other things to my list. I like lakes and oceans, so I can swim. I like to hike, so I need to be near mountains. And I don't really do well living in cities, which is why I don't live in Philadelphia right now. So I can start making lists of what I like and what I don't like in order to model my suitable habitat, maybe where I'd be happiest. living. I bet I could find plenty of areas in the Northeast, maybe even the upper Midwest, that would satisfy all of these points, meaning I would be happy living in these areas. They're good habitat for me. So you could do this exercise yourself. Maybe you're concerned about good school districts for your kids. You use lots of these criteria to buy a new house, purchase a new property. But while I can ask you about your preferences, we can't ask a chestnut tree about its preferences. So we need to do a little bit more detective work and find this out ourselves by considering lots of different factors. We call these environmental variables or habitat criteria, and using these spatial statistical models to see which of those habitat criteria are better predictors of suitable chestnut habitat. Is soil a good predictor? Is elevation a good predictor? Is rainfall a good predictor? These are the kinds of questions that these models help us to tease apart. So what we're doing is something called species distribution modeling, and you may hear Alec or I refer to this as SDM in this presentation. There are lots of flavors of species distribution models. Alec has actually run a whole suite of them. I think it's 10 at this point. So he can compare different models and map outputs to see where all the models agree that this is good or not good chestnut habitat. That adds robustness to the models. So broadly, species distribution models look at the relationship between known locations of a species, so where we know the chestnuts are, and the environmental characteristics such as soil type, elevation, rainfall, temperature, things like that, at those locations to predict the broader extent of suitable habitat. So we don't need to find chestnuts at every possible place in Pennsylvania. This saves us some time hunting around for them, but we are able to rely on great data sets like Sarah's provided us coordinates for mature trees from the dentata base in order to construct these models. So we need to know chestnut tree locations. Sarah's given us those coordinates, and we need to get a sense of these environmental traits, maybe things like soil moisture, temperature, rainfall, that may help to predict patterns of distribution. So really we can look at any factor, any environmental condition that might impact tree growth and success. So what's the soil type? What's the slope, elevation? We can record all of these observations, add them to this model, and look for patterns in the data. This allows us to paint a pretty good picture of chestnut habitat. So what this might look like from a little PowerPoint graphic that I spent quite a while getting my animations to work here. So let's hope PowerPoint cooperates right now. Let's say we've got a forest with trees in it, lots of different kinds of trees, and some of these are chestnuts. At those chestnut locations, we can measure or find relevant environmental variables like soil moisture and say, well, what's the soil moisture at the specific site where the chestnut is growing? Now I've got a graphic here where the brown sites are drier soils and the blue sites are wetter soils. And already we start to see a pattern. These 3 chestnut trees in green seem to be existing on the drier sites. Maybe that's a pattern that holds true throughout the whole state. We'd need more chestnut observations to find that out. Okay, the model takes this into account. We record values at those chestnut points, and we start considering other environmental variables as well. Maybe the next one we look at is slope, from steep in the red and orange colors to flat in the green colors. And here we're also noticing in this little graphic that chestnuts seem to be occurring on these steeper or mid-range slopes. Maybe slope is an important predictor because of this. We can stack as many of these as we want. Maybe I've got another parallelogram coming in for rainfall, another one for elevation, another one for canopy cover, et cetera, et cetera. You want to throw in 3 variables, 10 variables, 50 variables, you can do that. As long as you've got a reason for those variables potentially influencing tree growth, they may help to predict suitable chestnut habitat. So this is how we're building the physical model. We are throwing in a lot of these environmental predictor variables. We are recording the XY or latitude longitude coordinates of chestnut points from dentata base. And we're asking the model which environmental traits have the higher predictive power, which ones have low predictive power. And Alec will show you some graphs of the ranges within those traits as well. So we can draw conclusions like good chestnut habitat occurs at steeper slopes. And here's our graph that shows that's what our models spit out. We could also use these model results to predict suitable habitat elsewhere. So we can kind of expand this maybe south to Virginia and West Virginia, maybe north into New York. We can use this information to guide recommendations. So this work is not new. I'm not the first person to do it, but it was my master's thesis back in 2013 at Duke. This is what got me started on chestnuts. Is I did this work in Shenandoah National Park. I was an intern and I had an intern. I'm not sure how that hierarchy truly works, but she and I went and hiked a bunch of trails in Shenandoah, as well as using the Megatransect data set to locate about 50 large mature American chestnuts in the park. I used those as my input locations, grabbed a bunch of environmental variables, and was able to compare 3 different flavors of species distribution models to find the ideal habitat for chestnuts in Shenandoah National Park. Other folks have done this work as well. I was inspired by Songlin Fei, who's now at Purdue University. He did this modeling work in Mammoth Cave National Park in Tennessee and published a 2007 paper on this. Stephen Tulowecki at SUNY Geneseo recently, 2020, came out with a multi-model comparison of chestnut habitat using lots of species distribution models in Western New York. He also had a really cool witness tree data set, something I wish we had here in Pennsylvania, but he was able to incorporate that historical data into his models, which I think was really, really cool. And then even more recently, another Duke student, Paul Noah, did range-wide species distribution modeling for American chestnut. And Sarah, I believe you were involved with that project and that paper as well. So lots of people are doing SDMs. It sounded like from the chat, there are a couple other folks on here who are interested in habitat modeling or spatial statistical modeling SDMs for chestnut. Would love to chat more about this. Would love to get more SDMs up and running for different parts of the chestnut range. As we know, some of the factors that might influence suitable chestnut habitat might be different in Maine than they are in Georgia. So I think it's important to keep doing these models, consider scale, consider location, and consider local habitat while we're doing them. So I think my last slide coming up here before I turn it over to Alec is to really narrow down on our specific research goals. In our habitat models for American chestnut, our goal is to locate the best, the priority American chestnut habitat across the state of Pennsylvania. And we are doing that using a spatial statistical model, species distribution modeling. And for that one, we're specifically using an SDM called MaxEnt, or maximum entropy modeling. Alec has employed lots of other different models as well to compare the results or the functionality of different models to see if they agree or disagree in certain sites. Our main research questions are: what environmental characteristics predict the best chestnut habitat based on these existing chestnut locations? And how does spatial scale and model extent influence these results? So with that launch pad, I'm going to stop sharing my screen, and I'm going to, we'll have a minute or so, we'll play the Jeopardy theme song or something, and we'll let Alec share his screen and talk about the actual study. He's done most, if not all, of the modeling, the GIS, the statistics work on this. I just sit back and read his writing from time to time. So oops, I want to give him a lot of credit for doing this work. Okay, I think I've stopped sharing. I see myself again. So
Hey.
Alec, all you.
Yeah, thanks for that. And let's see if this 2 years of Zoom experience pays off. We can. All right, that looking good? All right,
Good.
So just as a reminder of the goals of this study, I wanted to use SDMs, or species distribution models, to determine both where suitable chestnut habitat is in Pennsylvania, and also to determine what kind of environmental variables make up that suitable habitat. And to do that, I wanted to explore how changing model parameters changes the results. It's important to remember these SDMs, in the end, they're predictions. It's not set in stone, it's not definitive. These are predictions of suitable habitat. So any ways to increase accuracy, increase confidence in these are useful. So to do that, I wanted to look at how varying extent and spatial scale resolution affected this. So we looked at modeling the entire state of Pennsylvania at a very coarse resolution. So we looked at the full state with pixel size of like 238 square meters. So large extent, but pretty coarse data. And then we picked out French Creek State Park as a local area to do more detailed modeling. So French Creek State Park, much smaller area, but we used fine scale 3-meter resolution data to look at that. And as Jen mentioned with SDMs, you need species occurrence points and you need environmental variables. So for these species occurrence points, Sarah was nice enough to let us use the database of citizen science collected chestnut locations vetted by experts at TACF. And then for the French Creek model, we were able to actually go out and do some data collection ourselves. So let's see, here's a map of the data collection at French Creek State Park. We went and took GPS locations 2 times for chestnut trees and chestnut sprouts. I ended up finding a bunch here. I think our final data set ended up being almost 300 combination of small trees and sprouts. So took the location, whether they were a tree or a sprout, the diameter at breast height, if it was measurable. And this first loop up in the northeast of the park, Jen and I went, I think in September, went and hiked that loop. And then I went back a couple weeks later in October, dragged my girlfriend along, who I believe is in the participants or in the audience for this. And we almost got rained on because I spent way too much time running through the forest and looking for chestnut trees and not enough time running back to the car. So in addition to those species occurrence points, you need environmental variables. So this giant table you can see is the environmental variables that I used for each of the models, the full state model on the top half, and then the French Creek model in the bottom. These variables were chosen based on previous research with chestnut species distribution models. So that Fay et al. Paper, Jen's paper, the Tilwecki paper, these ended up, we picked these to be, they are generally pretty predictively powerful for modeling chestnut habitat. And they're within sort of 3 types. You got land cover, topographic or terrain variables, and then soil variables. So you can see variable ranges within them. And we use most of the same layers for both models. We didn't include land use type in the French Creek model because French Creek was basically like 1 or 2 different land use types, so that wouldn't have been that illuminating. And then soil variables were different between them just because of that difference of spatial scale. We couldn't get the same soil data down to 3 meters, so we sampled from some. We took that from another database. Here you can see the initial, the model resolution in that second to last column, the full state model being 200, each pixel is 238 square meters. And the ones that are 30, we resampled up to be 238 because it all needs to be the same. And then in the French Creek model, down that really detailed 3-meter resolution environmental data. So what that looks like overlaid over Pennsylvania, here are a couple of the different layers of environmental data in GIS. So you can see slope varies from those dark greens, which are flatter areas, to reds along the ridge lines and peaks of the Appalachians through the center of the state. Elevation varies from lower elevations closer to black, and then higher elevations in white. I really like looking at these elevation maps because you can really see the stream and river networks. I think that's cool to look at. The land use map shows land use practices of Pennsylvania. So those reds are your urban and developed areas. The greens are more forest and open space. And then those browns and yellows are like agricultural and pasture land. And then finally, the sand to clay ratio layer is the sand content of the soil divided by the clay content. So generally is a measurement of how much sand is in the soil. And that varies from those darker areas, which are more clay, to those whiter areas, which are really high sand content. So along some of the ridge lines of the Appalachians and up in Pike County in the northeast of the state. So with the SDM we used for this part was Maxent, maximum entropy modeling, and putting all these together and a couple of model runs to actually make sure things work, you end up with something like this. So here's a map for the full state of suitable habitat in Pennsylvania as modeled for American chestnuts. These green pixels you can see are classified as suitable habitat, and those light blue are classified as not suitable habitat. You can see the spatial, the resolution and scale really come in here. This is pretty blocky, pretty pixelated, but you can still identify those large areas of suitable habitat. The table that you see in the top right, assuming that my camera isn't covering it, is a table of variable importance scores for essentially how influential, how important each environmental variable was in making this model. These values range from 0 to 100, with 0 being least important, 100 being most important. What you can see from this is that sand to clay ratio came out as the most important variable for modeling distribution of American chestnuts. 32.1, that's like by far the most important out of any of these variables. You can also see stuff like slope, pretty important, and then some of these topographic indices, which I'll talk more about later. But compared to things like curvature and distance to streams, those were less important. The two graphs that you see below this are response curves. So these essentially graph suitability for American chestnuts on the y-axis, and then these different environmental variables on the x. So that top one shows sand to clay ratio, the bottom one shows slope. So looking at the top one, you can see that as the sand content in the soil increases, so does suitability up to a point, and then it starts to decrease a little bit. And then slope, you can see at these lower values, suitability is lower, but once you get past about, I think this is in degrees. So after about like 15 degrees, chestnut suitability increases. Last thing to note on this slide, back to the table on the top right, is that AUC value in the bottom of the table. That refers to area under the curve, and it's a accuracy statistic for these species distribution models. That value will range from 0 to 1, with a value of 0.5 being essentially a random model that is no better at predicting habitat than just randomly guessing. So in general, AUC values from 0.6 to 0.7 are fair models. 0.7 to 0.8 are generally pretty good models, and then 0.8 to 0.9, excellent, and eventually to the hypothetical 1.0. So I then overlaid the suitability over an elevation map of Pennsylvania and rendered this in 3D, so you could see a lot of the trends with that elevation. So low habitat suitability are the darker reds, high habitat suitability as modeled here are those greens. So you can really see those high suitability along the ridge lines of the spine of Appalachia through the center of the state. You can also see areas of pretty high suitability in Pike County in the northeast of the state. That's where, if you remember back to that sand to clay ratio layer, there were really sandy soils. This was also breaking the state down county to county. This Pike County was the county with the most chestnut locations from the dentata base. Other areas of habitat suitability, if you look to where it says Pennsylvania in the title and go down, that patch there, I believe, is Allegheny National Forest. And then even though most of the western part of the state is predicted as pretty poor habitat, along the coast of Lake Erie in the northwest, there's a section of good habitat. Also, I was interested to see some of the areas around Philadelphia are modeled as pretty good habitat, where the surrounding agricultural land out by like Lancaster is worse. So this model performed well, respectable AUC value, but the coarse resolution, lack of detail, put some limitations to it that can be solved by fine scale modeling. So this is the French Creek analysis that we did. So much smaller area, but with a much more detailed data set. So 3-meter resolution for these environmental variables. This is a pretty similar slide that you can see to the full state one, but modeled for French Creek at this detailed level. And you can immediately see the difference in the amount of detail in the scale. With this, it's much easier to pick out the nuances of where there's suitable habitat, where there's unsuitable habitat. And you would be able to take this map, go to French Creek, and actually find some sites where you could then say, this is probably pretty good chestnut habitat, or I'm likely to find chestnuts if I look in these specific areas. Top right, again, you can see the variable importance scores ranging from 0 to 100. In this one, we see a little bit of difference in the important variables, which I'll talk about a bit later, but elevation came out as the most important in this one. Canopy cover also pretty important at 17.1. And then the soil variables, pretty important with soil description, field capacity, sort of as a proxy for that sand content. The variable response curves are those two graphs, bottom left and bottom right. And this is showing canopy cover on the bottom left and elevation on the bottom right. So with canopy cover, you can see as the canopy cover increased, so did suitability up to a point about 83, 84%, and then decreased a bit, where elevation, as elevation increased, so did suitability, and then it leveled off at the top. You can see the AUC value here was 0.94, which I was very excited to see. This is a very good model. This model took a long time to get right. With this really detailed data set, some of these modeling steps took a very long time. Some of the environmental variables generating that data in GIS, I had tools running on this computer for like 36 hours. The actual modeling itself took, running the actual model took over an hour, and then I had to redo it a couple times. But this, good to see that the work was worth it, and this is a pretty accurate model you can be confident in. So again, I overlaid this with an elevation map, and rendered it in 3D space so you can see these trends. You can see this, it's less exaggerated than the full state. Those hills of French Creek State Park are much less dramatic than the mountains of Appalachia, but even still, you can see some similar trends. In those higher elevation, those steeper slope areas, you see higher probability of chestnut suitability in that darker green. And then as you get to those valleys, those lower areas of dark red, that's less suitable habitat. And really here, I harp on this, but you can really see the nuance and with the detailed, smoother data. It's much easier to take this and be able to figure out where is actually suitable habitat on the ground. This map is a comparison of French Creek in both models. So that left pane A, is the French Creek model, fine scale, and then pane B on the right is the full scale model, but zoomed into French Creek State Park. And I just did this to highlight the difference in spatial in scale. So really that difference in using fine scale data, modeling locally for the French Creek model, and then for the full state model, that really coarse data, super pixelated. You would not be able to really look at that and see where in French Creek is good habitat. You could just generally say like, oh, in general, this area, big patch of habitat suitability. But as for the actual areas that would be good habitat to plant in, you wouldn't be able to tell that much. So in comparing both models, the left one is the large extent coarse resolution full state model. The right is that local extent fine resolution French Creek model. There's some pros and cons of each. Full state model, obviously, it covers much more area. And in doing that, it considers a wider range of environmental variables. This might be one of the reasons why we saw some of these different variables having different importances in these models. For example, in the French Creek model, we saw elevation was a really important variable, but in the full state one, it wasn't particularly important. This could be because elevation is only present in a relatively narrow range within French Creek. But when you expand that to that full range of Pennsylvania, there could be other factors coming in that are more have more predictive power than just elevation. So that could be where we see some stuff like slope come in, some factors like sand content in the soil, that could be different. Also at that, the resolution, difference in resolution probably changed some of these variables. So stuff like slope is going to be much more gradual when modeled over an area of 238 meters than just 3 meters. You can get some steeper slope values. Computationally, there was a huge difference in these models and was something that I wasn't expecting as much. The full state model was a breeze to generate environmental variables to perform the modeling. Like those steps in GIS were only like an hour or two at most, and the model itself ran within 10 or 15 minutes. Even though French Creek was so much of a smaller area, because the data was so fine scale, running that MaxCent analysis, the modeling took multiple hours. Generating those environmental variables, the one I mentioned before, ran for 36 hours. It was a hassle, but it was a lot more accurate. So that full state model AUC value of like 0.76, still pretty good, but we saw that local model with a AUC of 0.94 really outperformed it. So what comes from that is some different recommendations based on each model. This large extent full state coarse model may be better in identifying large patches of suitability. So you can look at that. You can look at, say, public lands, state game lands, state parks, and say, oh, in general, this public land is mostly good chestnut habitat. Whereas with the fine scale model, you can actually then look at specifically like that state park, that state game lands, and determine, okay, where in this area is the best chestnut habitat? Where are you most likely to find them? So that has been most of my work this year so far, is comparing those models. And that has all been performed with MaxEnt, maximum entropy modeling, which is one of these SDM approaches. More recently, I wanted to look at how different SDM techniques affect the model outputs. So there's this great package in R statistical software called Biomod, which lets you run a whole suite of different SDM approaches on the same data set. So I use the same species occurrence records from the full state model that I ran before. I use the same environmental variables. And after quite a time of bug fixing and fighting with my code, I eventually got it to run these 9 different models. They're just generally different mathematical approaches to figuring out species distribution, varying whether they use like statistical means or machine learning, whether they model linear or nonlinear relationships, and whether they can model interactions between the variables. In general, different math at figuring out suitability. This table shows all those different approaches. The names aren't that important for this purpose, but these are 9 different approaches, and then recorded to the AUC value, which is an accuracy statistic I mentioned before, and also TSS, which is another accuracy statistic. This one ranges from -1 to 1, with a value of 0 being a model that performed no better than random guess. Of this, the random forest, that RF model at the bottom, was sort of weird, showing values of 1.0 for both of those. That's probably not actually true. So I need to do a bit more digging on why that showed up that way. But of the other 8 models, we saw that GBM and MaxEnt performed the best out of those. GBM is gradient boosting model, whereas stuff like ANN and CTA, I believe artificial neural networks and classification tree analysis performed worse. So what you're then able to do with this is looking at modeling all of these factors over these 9 different models. You can see which environmental variables were picked out as more important by which models. So these are those same, I believe, 11 environmental variables from the full state model. And then I went and put in a table of the variable importance scores for each of the 9 SDM techniques. These values range from 0 to 1, with 0 being the least important or not included, and 1 closer to 1 would be that most important. And then I colored in, for each modeling approach, I colored in the 3 most important environmental variables as picked out by that approach. And their background is green if it was a positive relationship between that factor and suitability, red if it was a negative relationship, and orange if it was complicated. So the first thing you pick out from this is that Santa Clay ratio. In 8 out of the 9 models, not only was it identified as one of the 3 most important variables, but it was actually like the most important variable. And all of them identified this as a positive relationship. So in 8 of these models, they figured out as the sand content in the soil increased, as it became more sandy, the suitability for American chestnuts also increased. Topographic position index is another factor that was pulled out as one of the 3 most important by a lot of these. This was 5 models. It was in their top 3 and a positive relationship in all of them. Topographic position index is a measure of kind of landforms. So lower values on that represent valleys and sort of enclosed areas, where the higher values are peaks and ridgelines. So this shows that for those 5 models, as the landform became more like ridgelines, more like peaks, those high elevation areas, suitability also increased. Finally, topographic convergence index was the last one that was picked out as important by a couple of these. So 4 models identified that. and a negative relationship with it. Topographic convergence index is a measure of an index for soil moisture. So in these models, they all identified that as the amount of soil moisture increased, suitability for American chestnuts decreased. So what you can do after running all of these individual models with biomod is that you can actually combine them and combine their outputs and end up with something like this. So what this does is basically for each of those 9 approaches, they individually modeled where they think presences are, where they think suitable habitat is, and where they think unsuitable habitat is, in that binary yes, no. And then you're able to combine all of those and see where they agree is suitable habitat and where they disagree to increase the robustness and confidence in the model. So those dark green areas of this map, 7 to 9 of these SDM approaches all agreed that that was suitable habitat. And then as it gets lighter, fewer and fewer agreed. So in those lighter colors, only 1 to 3 models picked it out as suitable habitat, or no models at all. So what this lets you do is lets you be a lot more confident in your results. If you're just running one SDM approach and you see something marked as suitable habitat, that could be just a kink in the numbers, a weird way that SDM works. But if you're running it over all of these different SDM techniques and they're all agreeing that it's suitable habitat, you can be pretty confident in that area that that is truly suitable habitat. So this leads to a couple implications. Thinking back to that first part where we were talking about scale and extent, that large extent coarse full state model still produced good results. It was still a fairly accurate, that AUC value of 0.76. You can be fairly confident that those results were good. However, that fine scale local French Creek model outperformed it, performed exceptionally well, super high AUC value of like any of the SDMs I've ever run, even not on chestnuts. That's the highest value I've ever produced. And that suggests a sort of methodology for restoration and selecting restoration sites to first model extensively, but with coarse data over a large extent, and use that to identify general large areas of suitable habitat patches, and then selecting, say, state game lands or public held land that is present as a habitat suitability patch. And then you can go in at a local fine scale and model with detailed data the suitability there. And that will let you know the individual site-specific habitat suitability. It'll let you tell this is where we should go to in general plant chestnut trees that'll be suitable and they'll in theory be able to thrive. It's important to also include fieldwork and ground truthing these models. Again, these are not like definitive, yes, this is suitable, no, this is unsuitable. They're predictions. So you need to then, you can't just use these models to predict that. You need to use them to help inform your decisions, but that aspect of fieldwork and ground truthing is also critical.
All right, so just to wrap up here, thank you, Alec, for that great presentation of our models and our results. Ultimately, these models are one tool in the toolbox. They're, like Alec just said, they're not the absolute truth. We can't take them as an absolute yes or no, but they're very helpful for decision making. And what we need to do next is translate the results of these models to boots on the ground work, to locate planting or experimental sites to continue the chestnut restoration work. It's possible these models can be wrong in places. Don't sue me if that's the case. Oh, there we go. Thank you, Alec. So it's important to remember a couple different things. Species distribution modeling is just a prediction. It is based on the best available data. I like to say some models are wrong, or all models are wrong, some models are useful. Alex heard me say this a lot, is if you put crap in, you're going to get crap out. So we've done a lot of work looking at the GIS data layers that go into these models to make sure they are good data sets so that we can put our trust in the model outputs. But if the data going in is bad or not accurate, then the results coming out can't be trusted either. So models really only are as good as the data that are going into them. I started to answer some of the questions while Alec was talking. I didn't get to all of them, so we'll do a live Q&A at the end. But some data variables are also really hard to get. Things like soil pH are something that I would love to include in these models. It's just a harder data set to find, especially at the statewide scale. You might be able to get a more local data set, maybe for an individual state park or collection of properties, but sometimes soil pH is just not a data set that you find readily in GIS. If anyone has a good one, please point me to that. I've been relatively unsuccessful finding good fine scale pH data sets. It's probably important to chestnut growth, but it's hard to feed into these models just based on the format. So in conclusion, mixing all kinds and flavors of studies, different SDMs, different kinds of models, different GIS work, in addition to field studies, experiments, lab work, all of this is needed to prepare for reintroduction. It's not just the modeling, it's not just the field work. It's doing all of this at once, looking at the results as a whole, and using all of those experiments and results to make the final decision. So I'm really stoked to be one piece of the puzzle, certainly not the definitive piece of the puzzle, but I'm hoping that these models can provide some decision-making ability, some aid in where we restore chestnuts in Pennsylvania. So with that, we are finished. Alec and I are happy to answer any questions. I think it's about 12:30, so probably live is faster than typing some answers.
Typing it out, yeah. Jen, Alec, that was fantastic. I've had several people in the chat and in the Q&A to say you guys did a great presentation. Alec, Robbie says you have a wonderful future. I agree. This is really, really great stuff, you two. Thank you for putting it all together. The questions in Q&A are super meaty, so this may take a while, even live. Our audience has asked some really good in-depth questions. Sean Hammond asks, given that it has been 100 years since chestnuts were effectively removed and are no longer the dominant species in the forest, should reintroduction be thought of as an invasive species? And can we take advantage of what we know encourages spread of invasives?
I like this question a lot. I think no. I don't think enough time has passed to consider the habitat changed enough. Things like soil condition, the factors we're finding that are important, like soil, that's not something that would have changed so much with climate warming. Now, if temperature or rainfall, which we didn't include, elevation is somewhat a proxy for temperature, and rainfall and aspect is somewhat a proxy for rainfall. Those could be variables we include in future models. And if they come out as some of the best predictors, then that may be something to take a look at. But I think as it stands now, with soil being just the dominant driver of so many of these models, that we wouldn't gain anything by treating it like an invasive species. I think we can treat it like a native tree.
There's some really interesting.
And welcome for differing opinions too. Yeah,
there's some really interesting SDM approaches with that climate change, and I think the Paul Noah et al. Paper does that with the range map. It was something I was initially planning on including in this thesis, and then there's just so much research. I didn't have time to get into it, but you can, with these models, project their results onto future climate scenarios. So that's what some of the work has done to see how the range will shift over time.
Great, thanks. You brought up the NOAA model, which was great. It was one of the first time, I mean, from a practical applied standpoint, I've always known, quote unquote, that sand was really important. It was just something that you can see when you go out there and you're like, so behind my house is Game Lands 176. It's sandstone, there's sand everywhere. It's almost like a beach for central Pennsylvania, but American chestnuts are literally everywhere. And so the NOAA model showed like 25% to 75% sand being that range. And I get it, like even above 75% now, you've got too much, not enough water holding capacity for chestnut to grow there. I've had a couple questions about how do you define sand to clay content? How does that relate to percent sand content? Can you address that?
Sure, yeah, we took a ratio of them to avoid including two variables. They are correlated. So one of the first checks we go through in these models, if any variables are very highly correlated, statistically, it's not a good idea to include both. So you tend to choose one. So what we did to avoid that with sand and clay, higher sand, lower clay, it tracks pretty linearly, is to do a ratio of the two. I had previously modeled with the Shenandoah work percent sand only, with similar results. The higher percent sand content with more, I think I got similar results to the NOAA paper, higher confidence in sort of the 50 to 75% range, and got a little fuzzy towards almost entirely sand soils, but low predictability at low sand. So we just took the sand content of the soil for the large state model. This is a world soil database called ISRIC, ISRIC. And for the French Creek state model to get the fine scale data, and these all have layers like percent sand in the soil, percent clay in the soil, and at different depths. for the fine scale model, the USGS it's actually a vector layer that we converted to raster. It has a database, the Sasurgo database. We went through those data. They do it by county. So grabbing 2 counties, Chester and I think Berks is where French Creek is, was a much more achievable workflow than grabbing every county in Pennsylvania. If we had more time, I've had Alec for a year on this, so we've kind of had to pick and choose what we go for sometimes. That's a finer scale data. It's a database that the USGS maintains about soil content in the soil. So we were able to, or sand content, clay content, silt content in the soil. We were just able to basically divide sand by clay to get that number.
Excellent. And you guys have done a tremendous amount of work in just a year. So kudos.
Alec has.
Great work. Jim asks, RTK GPS ? Precision GPS ?
We have one. We were not able to use it for data collection at French Creek. We were going on iPad GPS accuracy, which was somewhere in the range of 10 to 15 feet most of the time. I think that was right, Alec. You were driving most of the time.
Yeah, it was mostly within that. All of it was under 30 feet. Most of it was in that 10 to 20 feet of accuracy.
Okay. Kim Steiner asks, land use type makes sense if you want to model where chestnut occurs now, because it is obviously not to be found on cropland, for example. But what if you want to predict what sites could be successfully reforested with chestnut?
Alec, do you want to take this one? You want me to take it? I see you're
so,
on mute.
Yeah, we played with land use stuff a while this semester. We have a data set actually of historical land use classification. I think it goes back to like 1920 might have been the oldest projected land use. So we thought about including that because obviously where chestnuts are showing up now is where they were back then. So even if you have like agricultural land from the 20s that's now forest, you probably still won't see chestnuts there. But the complications of adding that and the current land use data set just ended up not being feasible for this year. But that would be a cool addition to the project. Then eventually, with this modeling, we kind of tackled 2 approaches of like modeling at the same time where to find chestnut trees and where to plant them, where in actuality, those models are probably a bit nuanced and different. But I think what we did generally accomplishes both at like a fine level, but for modeling where to replant them, it'd be hard because the current data sets are all pretty historical. But that would probably be some nuance, some different data sets for that.
Well, and I think so. The Tolowicki paper starts to give that this historical locations with witness tree data, and I see Joyce Klaus is in our audience, and she's doing modeling in Georgia using some witness tree data, which is really great. I'm excited to see what they do with that information. So and Jen, I just talked to you recently about doing that in Ohio. So I think as we can put in those historical information, and yeah, those land uses don't go back far enough, at least in the digital world, to do that analysis, but that's really important to get to that. Thank you guys.
Yeah, that temporal limitation is a big one.
Yeah. All right, Sean Hammond. Oh, I want to get to anonymous attendee. I wish I knew who asked this, but hi, Alec. I was wondering if Villanova offered an environmental engineering major. If so, how does it compare to environmental science? What do you enjoy and not enjoy about computer science?
Yeah, so they do have an environmental engineering program. I think it's with sort of almost combined with civil engineering. I don't know a bunch about it, but I see them out doing some similar work as environmental science. They're in the wetlands a lot with their hard hats and digging up soil. But yeah, I've really enjoyed like environmental science and then the computer science minor here, because it seems a lot the way that the science is going, and with environmental science especially, where you have to model some of these really large scale trends, computer science is kind of the future of where that's going. So having a background on it has been really useful. The minor is pretty big. It's like 8 courses, I think, but it set me up really well to be able to, especially with ArcMap, be able to troubleshoot stuff a lot better. You have to get really good at Googling weird bugs and bug fixes. But then with our statistical software, which has been fantastic and was how I ran those 9 different models at the same time, I don't think I would have been able to do that without this computer science background.
That's great. Thank you, Alec. Mark says, great presentation, Jen and Alec. Have you studied how the co-occurrence of other species like beech, black cherry, American tulip, shagbark predict the existing success or planting site suitability of American chestnut from a correlated and/or causative standpoint, i.e. co-occurrence of various specific tree species as a predictor similar to the importance of, say, sand clay, soil ratio, or slope percentage? Thank you.
So we have not, but I think that's an avenue for future research. And some of those field experiments looking at how well chestnut does when co-planted with these other species, I think will form the basis for some of the relationships that will then be fed into these models. So with the species occurrence data, I wonder if we can bump this up to assemblage rather than individual species. Because if I think about going out to French Creek State Park and mapping every beech or every cherry, Alec and I would be there all day and we wouldn't walk a mile because they're everywhere. So it's almost, in chestnut, one of the things I grapple with too is chestnut was a generalist species. It wasn't rare in its heyday. It's rare now because of the blight. So what these models don't consider is any genetic variability within the trees itself. That is just completely out of the scope of this analysis, but it's important. It's just not something these models can tackle. So we don't have that genetic piece. Why is this tree on this site surviving? Maybe it's not necessarily the site, maybe it's good genes. And we don't necessarily know that. We have to model the site. So that's where some of the error can come into the model as well. But I think you're getting at something with species assemblage, like maybe a maple birch beech community or an oak hickory community. Which community types is chestnut more, I don't want to say accustomed to, but where does it fit in? I think we can look at some historical data on the ecology of the tree to get at that, but I think that is an avenue for future modeling efforts, and it's how do we fit that? How do we feed that into those models? But I like that idea.
Yeah, great. And Bob again says, I'm finding my population, she's the one working on Kentucky. Okay. I'm finding my populations mapped to divergent habitat requirements and not quite sure whether to use the statewide model or switch to local mapping.
So with divergent habitat requirements, like something like low elevations and high elevations?
Might have to get her to elaborate on that.
Well, my answer, I guess, from this is both. I think, Alec pointed out the utility of doing both kinds of models, to start with that coarser scale to at least eliminate a good chunk of the area and then hone in on the sites that pop up as good habitat on the coarse scale and do the fine scale modeling for a little bit more definition. So I think the fine scale models might tease out some of that divergent preference, those divergent preferences you might be finding at the large scale. Certainly there's more variation in elevation across the entire state of Pennsylvania than there is across French Creek State Park. So we're looking at a range this big in Pennsylvania, and we're looking at a range of elevations this big in French Creek State Park. That has implications for the statistics, the ranges, the models, and is one reason we're doing both. Bigger ranges are better, finer scale is better. So we're dealing with a little bit of trade-offs here.
Well, I think we can take some of these, from an applied standpoint, when someone comes to me and says, so, and in fact, we have another member on here who says, how do I determine what part of my 600 plus acres is most suitable? Whenever I do that, I do a lot of the similar types of analysis you do. We know sand is really important. So I'm going to put a plug in for Web Soil Survey. Web Soil Survey is an incredible tool for the landowner. Note, it in itself is a model. You still need to ground truth it, but it's a great first approximation. You can go to Web Soil Survey, type in your address, draw a polygon around your area, and you can look at that soil sand content. I mean, that in itself will get you, 75% of the way, or whatever it is, 30% of the way to knowing whether or not that's suitable. And I do intend on writing a site selection manual for an upcoming issue of the magazine. So there are other things that we look for that these models aren't taken into account. But if you can say, where do I want to start planting in Pennsylvania? All right, it looks like these ridge tops, Pike County, I can narrow down. All right, what am I going to prioritize in French Creek? I don't want to plant in the lowlands with limestone geology, blah, blah, blah. And then you could go even farther and look at these more finer scale points. Anonymous attendee says AUC is somewhat marginal, especially given the large scale. Did you do validation with Boyce's index?
I don't know what that is, so no. So limits my statistical knowledge.
All right, hopefully someone will elaborate on that.
I'll have to look that up. Some of these, the accent is Bayesian. So I guess it can use AUC, but it doesn't use traditional p-values. So there are slightly different ways of assessing performance when it's Bayesian.
Another anonymous, maybe the same anonymous attendee says, what do you think elevation means? For example, is this an indirect variable and a proxy for temperature or soil types?
I think it could be. I think it could be both. So they did not have high correlation with the other variables we used. Alec did his due diligence and checked those correlations. But I think it has been used in many other studies, chestnut related and not, as a proxy for elevation. Whereas I think someone asked about north and south facing slopes, that was accounted for in aspect, which was transformed from a cyclic to a linear variable just for statistical modeling. That can account for moisture content as well. Northeast slopes tend to be cooler and shadier than southwest slopes. So we're kind of getting at the temperature and moisture aspects from a few different angles using these topography variables.
I have a lot. Hold on, kiddo. Sorry, my daughter's home for Good Friday, and she wants to watch the next cartoon. A lot of people are talking about cardinal directions and orientation and aspect and slope, and there's a lot of other variables. I think you've addressed some of that already in terms of why certain parameters are chosen. I don't know if you can elaborate that, maybe specifically talk about cardinal directions and whether that has any implication.
Sure. So I think when Alec and I went about choosing our variables, this was a longer list than what ended up being included. And we think about what have other people used. So we've looked at papers like the Fay paper. I looked at what I did myself back in 2013, and I looked at a bunch of papers back then at Duke as well. We looked at more recent papers, the NOAA paper, Tulawecki paper. And we thought about what environmental conditions might influence a tree's growth or survivability. So if I were a plant, and in my next life, maybe I will be, what will make me happy? Is it the type of soil I'm growing in, the moisture content, the elevation, the slope, the face of that slope, which is aspect in our models, aspect of the slope? Is it things like temperature, range, moisture? So we can think of a whole suite of things that might affect how, quote unquote, happy the tree might be at a particular location. Some of those raw variables are harder to get than others. So temperature models tend to be pretty coarse over areas. They fluctuate readily. So we'd have a choice, like, do we want to do coldest temperature in January, warmest temperature in July? Other models have included those data. We didn't here. We chose more topographic flavored variables like elevation, aspect, slope. So yes, we could include those variables as well and see how they shake out in model performance. Some of this was a time issue. Some of this was a correlation issue. But a lot of the indices that were in Alec's list, things like topographic convergence index, topographic position index, a lot of these address, they're indices that I did not create. There are other papers, other scientists have created these indices to account for terrain and moisture in the same index to kind of get that hybrid approach. So if it's a convex versus a concave slope face, you're going to get different water holding capacities, different water retentions in there. So we included things like those because we thought they would be maybe a more relevant environmental variable to model tree habit and tree growth and how the species might perform. That's kind of our decision-making process going through. Yeah. There's room to include other things, absolutely. I think the pH came up. I think that's just hard to find.
Well, and there's lots more modeling that can and should be done.
Yes.
I mean, there's lots of area to cover. So I want to tell everybody that, one of so I think John Scrivani's on this call. He helped you, I think, Jen, when you were working in Shenandoah. He's an amazing GIS whiz, and he's now the chair of our restoration committee. And these models are a big priority for us. Trying to figure out these decision-making tools, making them available to landowners, private landowners, as we embark on restoration is a really important priority of the foundations moving forward. So expect a lot more of this to be available and in a lot more different locations. Excellent, thanks, Jen. Doug Boucher. Doug, I haven't seen you in a while. Good to see you on here. Jen, can you tell us what is the basis for the nearly 4 billion estimate of the number of chestnuts before blight? Is it derived from the old, now disproven estimate that chestnuts made up 25% of the eastern deciduous forest? Do your GIS results help come up with a better estimate of the population at different times in the past?
So I don't know what the basis of that 4 billion estimate is, Sarah. I don't know if you have any additional
not been able to find it, to be quite frank.
Yeah.
It's something that we've
heard
looked
it.
for to see where that came from. And I want really quick, I want to address that 25%. So chestnut was 25% of the forest in some areas. It was 50% of the forest in some areas, but it certainly wasn't across. Whenever we show that range map, it wasn't 25% across the entirety of that range. It really varied based on a lot of different factors, as you see here. So I wouldn't say that number is exactly disproven, but it's more subtle than it's 25% of the whole forest. So I wanted to address that, but then yeah, the 4 billion, I don't know. We have tried to figure out how to do that. Can this modeling help get to the basis of that?
So I think the flavors of models we're running, likely not. We're looking really at a snapshot of the present, and if we were to add that climate change lens, so I call them hot layers, the increased temperature predictions for the area, maybe variable moisture regimes predicted for the area from the, I've used IPCC scenarios in the past, is a forward look. The past look is a little bit harder because of the availability of historic data in a GIS spatial environment. So like we were talking about with the land cover before, it might go back to, in some cases, the 20s or the 30s. But we really would like it to go back a little bit further to paint a better picture of the landscape back then. And since they didn't have ArcGIS Pro or high-tech GPS units, or, you know, they were experimenting with flying drones back then, actually, but nothing as sophisticated as we have now. It's just really hard to get our hands on any reliable data sets, which is why I'm so excited about witness trees and including those. I think that's our best shot of getting even close to any of those numbers, including them in the models, using them to predict forward. I wish we could jump back in time and get a better handle on that, but I'm not sure these species distribution models would do so well looking backwards rather than looking forwards.
Very, very cool. I want to get to another one of Doug's questions. He says, Alec, can you tell us about the sample sizes that are the basis for these models, both state and local? Related to that, is it possible to say which relationships that come out of the Maxent model are actually significant given those sample sizes?
Yeah, so for the full state model, I think from taking chestnut locations from the dentata base, clipping them down to just pure Americans, and then clipping it down to Pennsylvania, I believe there were about 250, 260-ish within the state. And then for French Creek State Park, we went out and collected field data, ended up having around somewhere in that 300 to 350 chestnut locations. Although clip that down to just to not include any sprouts that didn't have a measurable DBH. So probably 180-ish there. So those were sample sizes. The way that these models work, because they're Bayesian modeling, it doesn't, Jen can probably explain this a bit more with the statistical background, but they don't have like measurable p-values to say whether it's like significant data or not. So the results are a little bit harder to tease out with that in that way.
Thanks, Alec. It's hard to go between and forth like typing and then asking these questions. BlackRock asks, do you have a model with a vector map layer over that raster most suitable layer that you had up? Just asking because I was having a time of locating my farm with just the topography when you had it. So I think this person is asking, can I use this? Because I'd really like to use it for my farm, and how do I do that?
Yeah, so we can, I would say at the something like the model agreement, Alec had the, you know, the 0 to 3 kind of in those bins, or the thresholded layer. So it would be easily convertible to a binary yes, no at a 50% threshold. That's easily vectorized. And that could be overlaid. You know, I could work that up in ArcGIS Online today even with the vectorized form. The rasters are a little touch and go in ArcGIS Online. Esri hasn't quite figured out that portion yet. I am a tester for that at Villanova. It's still yikes. But vectorized layers, yeah, we could get that mapped in something like ArcGIS Online. That's a platform I'm most familiar with. So you could zoom in and look, does your property, is it in the yes area or the no area?
And I think that's a great first step too for folks. And again, like you said, that doesn't mean it's absolutely not or absolutely is, but it's a great first step. If it looks like yes, it is, you can hone in on that and do some of these more fine scale, like on your own, go to Web Soil Survey, or wait for us to do some of these finer scale models at higher resolution.
And think of it as likelihood. It's Bayesian, so it's probability and it's likelihood. If we had, I think Alec, you split it at 50%, just to know, right at 50, we could split in splits. And so in showing the raster, if a particular pixel in the raster had a value of 0.9, that's a 90% probability. So you'd be a little more confident in a pixel with that value than a pixel with a 0.6 or a 60% probability. So we cut it off to make it a little bit more visually pleasing in a map, and that would be the version that's easily vectorized. But we could go in and assess from 0 to 100%, what probability does this model predict a particular site is for chestnut suitability.
And I want to point out, so there was a question about I think Doug asked that question about sampling, and I'm talking a lot about my own work, which I don't normally do, so I'm sorry for doing that. But in the upcoming magazine of the Chestnut Foundation, another Duke Standback intern, Jack Alcorn, worked with us in 2020. Yay, Duke Standback interns, of which I am one. So we looked at tree snap, iNaturalist, and Dentatabase, and all those 3 different ways that we've captured points of American chestnut. And what's really interesting about Dentatabase, those 200 some points, they are by far skewed to being larger trees that are fruiting, because that's what we're interested in. So that's the sampling. If you take into account tree snap, you tend to get many more of those smaller types of trees, like what you were finding there at French Creek. And then iNaturalist is really there's no size information, so you can't really go on that. But there's a lot of really interesting aspects to consider when you're looking at these different citizen science collections of points and samples. But I did want to address that. So if you check out that article, it talks a lot about the differences of these trees, what's contained within these databases, and how we can use them in different ways. I want to do one more question. I know we're almost at 1 o'clock. Before I do that question, and we lose any more people, so next month, May 20th, we're doing something called Seeking Clarity. We have a great panel: Andy Newhouse from ESF, our own Jared Westbrook at TACF. James Votaw is a regulatory lawyer with Keller and Heckman. And then we've got, I can't remember his name, but he's a representative from North Carolina Biotech. And then yours truly will be moderating the discussion. We want to talk about what do we know? What do we not know? What can we not know until we get trees in the ground? I mean, really wrestle. We did a big questions last March. We wrestled with some of these more philosophical questions. We're going to continue that discussion with, like I said, regulatory law, policy, government and policy, and the science, where all those kind of intersect. I'm going to segue to say all of that talks about prioritization of site. So I had a couple of questions in here, about how do we prioritize, so we had that question from Kim and another attendee about farmland. How do we know there's no trees there? How do we know whether it's suitable or not? We had a question about, can I access it? Accessibility, like, is it close to a road? Is it too rocky? Like all that stuff. So, when you start talking about, and when we start talking about too, land ownership, public versus private, or maybe we start talking about sovereignty of indigenous peoples, and whether or not, our planting locations are within or beyond that boundary. How can we proceed with modeling some of these more sociological aspects that go into the restoration program?
Yeah, so as for a lot of those, like land ownership and stuff, these species distribution models, like they look great, the output is cool, but in the end, they can be a step 1 for further research. I know that Tilwecki paper that we were talking about compares his results to public versus private held land. So you can take these suitability layers that are generated in GIS and overlay them with land ownership. You could overlay them with indigenous land, with land use types, to do then further analysis on, if you can only replant in public land or private land of people that volunteered up, you can narrow it down to just those potential areas and then look at the suitability within those areas.
Great. Well, the top question just popped up of how are we going to do this beyond Pennsylvania or French Creek? There, like I said, there's a lot of interest. Anne says, she's got one for Kentucky. We've got a couple of other models that are in the works. Like I said, Joyce is working on Georgia. We've got a couple of broad scale maps at the range wide level that are available and can be used. And we've got lots of interest. Like I said, we're working with some folks in Ohio to develop one in southeastern Ohio that can be used beyond. So there's a lot of real great interest. TACF is prioritizing this work for private landowners. And I had another question pop up from Mark about how am I as a private landowner going to do this? And, you know, there's a lot of, once you get the site, that's the first most important aspect. Then you got to say, what's my deer pressure? What's my competing vegetation pressure? What are the invasive species that I'm going to have to deal with? Sunlight, you know, none of those have really been taken into account in this particular model. And those are sort of, now you talk about installation, best management practices, maintenance, all that kind of stuff. That's another factor that TACF does have some really good BMPs established that we can make available or are available online as we embark on restoration. Jen, Alec, great work. Thank you for sharing your information and for being amazing, charismatic guests. And I've really enjoyed our conversation. Lisa, any final words?
Nope, just thank you, Jen and Alec. It's amazing. I'm so inspired. There's hope to get that tree in the forest and have it actually survive. Wouldn't that be fun? There's some great comments and accolades in the chat for you both, so maybe take a look at those before you hang up. Happy Passover, Easter, Ramadan, lots of religious holidays this weekend, so enjoy and stay safe out there.
All right.
Thank you so much for having both of us. I'm a slow reader. I'm trying to address the chat before I sign off, but my email is in the PowerPoint. If you also Google my name in Villanova, I'll come up. Feel free to email me. I'm pretty glued to a computer, as might be evident from this work. So I'm happy to chat further at a later date or time.
Thank you all so much for inviting me as well. This was a good, really fun presentation, and honored to be invited. And yeah, my email and contact information is also in that PowerPoint. I think it's also in the events page. So also, if you have any questions for me that we didn't get to or want to get in touch, feel free to email me there.
Alec, this was your first time presenting this information?
Yep. First of 5.
Yeah.
Great job. It'll get better. You set a high bar to improve from here. All right, great. Well, I'll look forward to talking with you in the future and seeing more great work.
Thanks, everybody. Thanks to the participants. Appreciate you.